Welcome to All Things Data. Today we're going to explore K Nearest Neighbours. All code and resources are linked in the description below so you can follow along. Let's get started. K Nearest Neighbours is a fairly simple and straightforward machine learning algorithm. It is non-parametric and supervised. The core idea is that data points that are close to each other in the feature space usually have similar labels or values. K Nearest Neighbours also has the advantage of being capable of performing both classification and regression tasks. The first step in the KNN algorithm is to select the data point you want to make a prediction for. This point should contain the same features as the training data, but without the target value. You also need to decide on the number of neighbors, k, to consider. Next, calculate the Euclidean distance between this point and all the points in the training dataset. Then, identify the k closest training points by sorting the distances in ascending order and selecting the top k with the smallest distances. Finally, use these neighbors to make a prediction. For regression, take the average of their target values. For classification, you can choose the most common class among the neighbors. This result becomes your prediction. If you didn't fully understand the algorithm, that's fine. Playing around with this visualization will help make things clearer. The following is a dataset where we use KNN regression to predict body fat percentage. Play around with K. The first thing you should notice is that as we change K, the prediction changes. You will also be able to find a table of the closest neighbors. The code for KNN regression is straightforward. You simply load the dataset and choose the features and target. The only parameter you need is n neighbors, which represents k. And on the bottom right corner you can see the printed prediction. For classification, the steps are almost identical. However, the target must be categorical. In this dataset, we want to predict diabetes using glucose and age. The main difference is instead of using K Neighbours regressor, we use K Neighbours classifier. The class label is 0, meaning it predicts no diabetes given the test data. As explained earlier, the number of neighbors is a mandatory parameter. An optional but useful parameter is distance. By default, if weights are not specified, all points are weighted equally. However, when you set the weights to distance, closer neighbors affect your prediction more. As with all data, make sure you clean it thoroughly by checking for missing values, duplicate values, outliers, and inconsistencies. Since the K Nearest Neighbor algorithm is based on Euclidean distances, it is important to scale the features. Typically, we use standardization, but there are certain cases where we would use normalization. When data does not follow a normal distribution, it is highly skewed or has a bounded range, then normalization is preferred. The most difficult part of utilizing KNN is feature selection. Including the wrong features can make the model useless. A good first step for feature selection is to remove irrelevant features such as name or ID. As with all datasets, performing EDA is crucial. The second step is to remove features with little or no variance, since they do not help with prediction. You can identify these features with various plots. It is also a good idea to remove correlated features. To identify them, use a correlation heat map. There are no hard rules on which correlated features to remove. Each case is different and you have to use your own judgment and understand the trade-offs. That being said, the ideal feature to remove would be the feature that has less correlation to the target, has more missing values, and is less interpretable. More advanced feature selection techniques can be applied, including statistical tests, wrapper methods, and dimensionality reduction techniques. Choosing the ideal k is also another issue to consider. In order to find the best k value, we want to choose a range of k values and calculate the average cross-validation score. Then we would plot k on the x-axis and the average cross-validation score on the y-axis. There will be an elbow point on the plot, and that contains the ideal k. On the left, we have a plot of k versus mean squared error, and we can see the elbow point is at 5. On the right, we have a plot of k versus mean accuracy, and the elbow point is 6. When k is too small, we run into the issue of overfitting, where there is low bias and high variance, as the model is essentially capturing noise. On the other hand, when k is too large, we have underfitting, where the bias is high and the variance is low. And this is counterintuitive to the concept of the algorithm, because we only want neighbors that are similar to the test point. The code examples previously mentioned is far too basic for a KNN workflow. To perform KNN effectively, it is crucial to first perform EDA to understand the data, then clean it. It may also be necessary to scale the features. Before running the algorithm, it is crucial to perform feature selection. Next, the ideal K must be found using cross-validation and identifying the elbow point. Lastly, you can run KNN using the chosen features and K value. The full code is linked in the description below. If there are ties in classification where there is more than one most common class, scikit-learn only takes one class. To avoid this issue of ties, you can increment or decrement K by 1. Another method is to use weighted distances mentioned earlier. Overall, KNN is a very beginner-friendly algorithm. It is easy to implement and has an intuitive algorithm. Anyone with knowledge of Euclidean distances, mean, and mode will be able to understand it. It is also a flexible model as it can be used for regression and classification. The biggest con is that KNN is outperformed by other models, but that is to be expected considering its simplicity. KNN also suffers from the curse of dimensionality, which means that if you have a lot of features, then the neighbors are all so far apart and become meaningless. To somewhat fix this issue, you could obtain more data points to make the space more populated. However, KNN is slow and memory intensive as it has to store all the training data and perform computation during each prediction. Lastly, KNN requires selecting good features and a K value that works, otherwise the predictions become meaningless. Thanks for watching and remember to hit the subscribe button.